RISC-V is an instruction set architecture that's released under an open source license. That means anyone can use it to develop a CPU without having to pay any sort of licensing fees. And it means we can run some of those CPU implementations on an FPGA to learn how a CPU works. In this video, I'll show you how to build an existing RISC-V implementation for the iStick and then use it to run some code. There are a number of great RISC-V implementations out there for the ICE40 FPGA. Claire Wolf, the original author of Yosis and Project Icestorm, has created her own RISC-V implementation called Pico RV32. It's quite popular, but it requires a few more lookup tables than we can spare on our tiny iStick. Bruno Levy, a director of research at INRIA in France, created this tiny RISC-V implementation specifically for learning and tinkering. He calls it FemtoRV, and it's what we're going to use. If you go to the FemtoRV folder, you can find a tutorial specifically for the iStick as well as for some other FPGA boards. I'm going to be using this guide to install all the tools necessary to build this processor. Note that in addition to the FPGA tools, you also need a RISC-V compiler so you can build C code for the processor. It seems that all of the RISC-V FPGA projects I came across rely on Linux for installing these tools. While you might be able to get this to work on Mac or Windows, I'm going to use Raspberry Pi OS to make this process easier. Feel free to look through this guide as well as the other files in the repository. RTL in the FemtoRV directory contains the Verilog code for the processor. SoC stands for System on a Chip, so FemtoSoC is the top-level design for the project. This is where the processor is instantiated as a module and connected to RAM, program memory, and the various hardware peripherals, which are called drivers. These are things like UART, SD card, and LED drivers. If you go into the Devices folder, you can see the various peripheral drivers. We'll only use a few of these as our iStick has limited space. Finally, if you go into Processor, you can see the various implementations. We'll be using the Quark version as it's the smallest. It leaves off a few features like interrupts. We're not actually going to get into CPU design in this series, as that can be an entire college course. I'm just going to show you how to use someone else's design and connect custom hardware modules to it. To start, I've SSH'd into my Raspberry Pi so that you can see what's going on. I'm going to create an FPGA directory that I can do most of my work in. I'll navigate into that directory, and then the first thing we want to do is to clone Bruno's repository. Before installing any packages, I definitely recommend doing an update to the package manager, and I'm going to do that with sudo apt update. Once that's done, I recommend going to Bruno's tutorials in the Learn FPGA repository. Here you should find a link to the iStick tutorial, assuming this is your board. If you have another board that's listed here, I would do that. Otherwise, you might have to port the design yourself. So let's go to the iStick tutorial. Scroll down on this page, and you should see a link to directions to install the FPGA development toolchain. Even if you installed Yosis and Project Icestorm before this episode, there's a chance you might need to do it again because we're going to be installing a bunch of other tools to go along with it. Scroll down on this page. You can see the directions to clone this repository, which we already did. And then we need to install Yosis. And we're going to build it from source. So I'm going to grab this command that installs the dependencies and paste them in. This will probably go a lot slower for you because I already have these dependencies installed. Next, we're going to download the Yosis repository, and we're going to build that one from source. This is, of course, assuming you don't already have Yosis installed. Note that if you installed Appio, there's a good chance that Yosis is not on your path, so you can't call it directly. Hence why I recommend doing this again, even if you installed Yosis through Appio. Navigate into the Yosis directory, type make, and you're going to let that run for quite some time. When that's done, we need to install Yosis on our system. Call sudo make install, and that will copy the necessary files so that you have access to this tool. Next, we want to install Icarus Verilog in case we want to do any sort of simulation. I'll go ahead and install that along with Verilator, which we haven't been using in this series, and we can drop back to the FPGA directory. Scroll down in the tutorial and you can see that we've done all these steps, including installing iVerilog, which is Icarus Verilog, along with Verilator. We also need to install Project Icestorm. And to start that, we need a few dependencies. So I'm going to copy this command and run it. Once again, this will probably take a lot longer for you, but I already have these installed on my Raspberry Pi. Then we can clone the Icestorm repository on our system. We want to go in there, and we're going to call make-j4, which says to run it with 4 threads. That should be good enough for our Raspberry Pi. Once again, this will take some time, so go make a sandwich or get some coffee. Once it's done, we'll want to call sudo make install so that we can install Project Icestorm on our system. Let's leave that directory, and we're going to do the same thing for Next PNR. We'll call git clone -- recursive so that it also installs all of the submodules in this repository. We'll head into the Next PNR directory, and we need to call cmake with a very specific list of parameters. So I'm going to go into the tutorial and find the Next PNR section. Here it is. It specifies the architecture as ICE40 and the install prefix as user local. So I'm going to copy that, paste that in, and let it run. When cmake is done, we are going to call make again, and this time we'll let it run with 4 threads, just like last time. Once that's done, as usual, we will call sudo make install. That will install Next PNR on our Raspberry Pi. While that's installing, let's take a look at the tutorial. We've just installed Next PNR, and as you can see here, in order to have the Raspberry Pi, or most Linux systems, at least those that use UDEV, in order to have our Linux system talk to the FPGA, or the iStick in this case, we need to add a rule in the UDEV rules. And this is assuming you are running some flavor of Linux that uses UDEV. We're going to copy this rule. We're going to go into our Linux terminal, and we're going to create a new rule in udev rules.d, and we're going to call this one 53 lattice FTDI. This is going to allow us to talk over USB to the FTDI chip on the iStick. I would paste this in here, but as you can see, I have already done that. This is just the rule I got from the tutorial, so I'm going to exit and save. Then we want to go into the femto SoC. Go into the Learn FPGA repository. Feel free to list the files there. We want to go into femto-rv, so cd femto-rv. Feel free to look in the RTL directory. We will be working with the femto-soc.v file, but before we do that, we need to configure a few things. So use your favorite editor. I'm going to use Nano because it's simple. Go into RTL configs, and we're going to go into iStick because that's the board that I'm using. Scroll through this and you can see all of the defines that are being listed that include certain functionality in the SoC or in the processor. First of all, even though we have an IR receiver and transmitter on the board, we're not going to be using that, so let's comment that out. I also don't care to use the driver for this OLED screen since I don't have one, and I don't have an 8x8 LED matrix. By commenting out these lines, we are telling the hardware or the synthesis tool that we don't want those peripherals to be built along with the processor. So that's going to save us some LUTs and some space, along with some I/O pins that we may want to use down the road. You can see that this section is commented out from these comment lines. We're going to be using the femto-rv32 Quark version, which is, I believe, the least amount of lookup tables being used for this particular implementation. This part sets where our program resides in SPI flash. Our program memory sits in the SPI flash chip that's outside of the FPGA. However, our RAM is made up of block RAM that's in the FPGA. This defines sets how much RAM we have. We can't do any more if we're using the iStick. 2K of this is set aside for registers that are required by the processor itself. We're left with whatever's left over. Since we start with 8K, 8K minus 2K gives us 6K for RAM. Then we have this setting, NRV run from SPI flash. Once again, this says not to use readmemh to set the firmware in block RAM as an initialized value, but rather store the program that we write and compile in SPI flash. So that's what this define is doing for us. Go ahead and save and exit. Say yes when asked. Now we need to synthesize the design and upload it to our FPGA. I'm going to go ahead and plug in my iStick into my Raspberry Pi so that when it's done building, it will upload to the iStick. Make sure you're in this learn-fpga femto-rv directory. You don't want to be in any other folder when you call this make command, and call make iStick, and iStick should be in all capital letters. Note that the very first time you run this, it will download and install all of the RISC-V development tools. So once again, this might take some time, so be patient with it. The good news is once those RISC-V tools are installed, you shouldn't have to run this part again. So when you call make iStick in the future, it will just synthesize your design and send it right to the iStick or whichever FPGA board you're running. Note that you shouldn't call make iStick, you should call make and whatever board is supported. Once you see this programming done, reading verify OK, bye message appear in the terminal, this means that the RISC-V processor and the accompanying hardware peripherals as part of that SoC top-level design have been synthesized, routed, and uploaded to your FPGA. So now you have a blank processor that's just sitting there in your FPGA waiting for some instructions to tell it what to do. At this point, we need to write some code and then compile it and upload it. Before we do that, I recommend going back to the repository to poke around some of the include files to kind of get an idea of what's going on. Let's head back to femto-rv. We'll look in firmware this time. And let's look in libfemto-rv32. This contains some very useful code, include files, and libraries that I recommend looking through. In particular, we want to look at the hardware config bits, and that's the header file. These bits are used to control your special purpose registers. Now, note that these registers don't actually exist in memory, they're just in address space. So when we write to a particular address, the hardware recognizes that we're trying to do something with a particular driver or peripheral, and it handles whatever you're trying to write at that address. These bits tell us the address that we need to write to. So let's go back. We're going to look at femto-rv32.h. If you scroll down, you should see the I/O listed here again. Those bit numbers that we saw earlier correspond to these I/O bits. The I/O base is the address of that imaginary memory space. So when we write something to hex 400000, we're telling it we want to do something with one of these devices. For example, turn on the LEDs, which is what we're going to do. Pay close attention to what's going on here. Normally you would call these macros I/O in or I/O out or LEDs, and it would handle writing or reading from the correct imaginary address or memory address that doesn't exist. It's really just pointing to a hardware driver. So we would take IO base, which is this hex 400000 number. It's going to then add it to the port, which is what we input here. And you would give the port as something like this, like IO LEDs. And so this says IO bit to offset IO LEDs bit, which if you remember earlier, IO LEDs bit is 0. Let's head back into that file. IO bit to offset is given by this macro, so 1 left shift 2 plus 0. So 1 left shift 2 added to 400000. That means the address for working with the LEDs is actually hex 400004. When we write to that address, that will tell the hardware driver that we want to control the LEDs. Let's give that a shot. Back in our terminal, we're going to go to that top-level FPGA directory, and I'm going to create a directory that's called femto rv32. This doesn't exist. I'm going to keep my software, or rather my firmware, in here. And I'm going to create a project called Blinky. Let's navigate into that directory. And I'm going to make a main.c. If you've done any sort of C programming, that should look very familiar. Lucky for us, Mr. Levy has included a header file that defines some very nice features for us to use in this femto rv32.h. With this, we can do all that memory mapping we just looked at, and it gives us access to things like printf, which outputs things to the serial console, or in the case of the iStick, out of UART through the FTDI chip over USB and to our computer. We will use a makefile that handles all of the linking for us so we get access to these libraries. We're going to create a super basic loop here. We're going to print something to the console each time through this loop. I'm also going to print out the frequency that the CPU is running at, just as a test. And this should be stored in the femto rv32_freq constant. Now, remember what I said earlier, that we write to this imaginary address. This memory doesn't actually exist. We're just addressing into this space where the SoC is looking for something to be written at this address, and it's going to do something with that value. In this case, when we write to hex 400004, that says do something with the LEDs driver. And in this case, we're going to write 3, which is binary 11, which says to turn on the first and second LEDs. 0011, so the first 2 LEDs are on, the second 2 LEDs are off. We do this by casting that address as a pointer and then dereferencing that value so that when we write something to that address, it's writing to that address in memory, or it's thinking we're trying to write something to an address in memory. That femto rv32 header file also has a delay function that we can use, and that handles just delaying the processor for 500 milliseconds. After that delay, we're going to then write 0 to that imaginary memory address to turn off the LEDs, and then we're going to delay again for another 500 milliseconds. Because I said main should return an integer, I'm going to say return 0, even though my program should never actually get here, and close out main. Let's exit and save. And now I'm going to create a makefile. To make things very simple for us, that repository contains a makefile.include file. We want to include that in our makefile, and feel free to use this makefile to set up your project or link any other libraries you want, but for this very simple program, we shouldn't need to include anything else. So all we have to do is point to that include file and then save and exit. Then we call make main, which is the name of our main.c file, but we give it the suffix .prog, which tells that included makefile that it needs to compile our code for the RISC-V processor and also program or upload it to our FPGA board, in which case our program will sit on the SPI flash memory and the CPU will read the instructions from there in order to execute them. This should be fairly quick because our program is pretty small. Everything should look okay. You should get verify okay and bye, which means it's done. It has uploaded to our FPGA. From here, let's install a serial terminal. In this case, I'm going to install Picocom. You can use Screen or anything else you want. And I'm going to call Picocom, give it a baud rate of 115200, and connect it to dev TTY USB. And this is going to be USB 0 or 1. In my case, it looks like it's USB 1. Just pay attention to what serial device your FPGA board enumerates to. So let's open that, and hopefully, if everything works, you should see Hello World followed by the frequency of your CPU being printed to the terminal. If you're in Picocom, when you're done, press Ctrl A and then Ctrl X to exit. And let's go take a look at our board. The first two LEDs should be blinking. That tells us we wrote to the correct memory address in our code to control the hardware. Your challenge is to get buttons working as inputs on the Femto-RV. You'll need to change some of the Verilog code as well as write a C program to test the buttons. I recommend starting with the Femto-SoC Verilog file. If you look at the port list, you can see where some of the buttons are defined depending on the board used. You can use the default buttons or define your own. If you look at the iStick PCF file, you can see that the PMOD pins were taken up by other peripherals. You'll need to disable some of those and add your button pins here. Note that the pull-up directive does not work in the PCF file due to how the build tools are used. If you take a look at this tech library document, you can find a number of directives that will work for the ICE40. In particular, you'll want to use the SB_IO directive that allows you to control the pin hardware directly. You can instantiate it just like any module, and you'll want to configure the pin to be a simple input. You can find an example call in this section of the document. You'll upload the changes to the processor first. From there, you build and upload your C program. For my test, I have the LED flash as long as the first button is held. I'll post a link to my solution in the description. Take your time with this challenge, as you'll need to read other people's code to get a sense of what's going on. Also, this is probably a larger project than what you might be used to, so it can be a little tricky to keep track of everything. Next time, I'll show you how to modify that processor to include your own hardware peripheral. Happy hacking!